Hello? Yeah, I can hear you. Can you hear me? That's super. Yeah.
Was with APB Scandia Randers, Denmark from 1987 to 1988. He got the PhD degree in electrical engineering at Aalborg University. He became an assistant professor in 1992, an associate professor in 1996, and a full professor of power electronics and drives in 1998 at AAU Energy. He has received 38 IEEE Prize Paper Awards and IEEE PELS Distinguished Service Award in 2009, the EPE PMC Council Award, the IEEE William E. Newell Power Electronics Award, the Willem Kahn Rasmussen Research Award, the Global Energy Prize, and got IEEE Edison Medal. He was the editor-in-chief of IEEE Transactions on Power Electronics from 2006 to 2000. Distinguished lecturer for the IEEE Power Electronics Society, he has been vice president of the Danish Academy of Technical Sciences. His current research interests include power electronics and its applications, such as in wind turbines, PV systems, reliability, power 2x, power quality, and editor of 14 books in power electronics and its applications. We are very thrilled to have you here with us, sir. So you may start the session.
Okay, thank you very much. Thank you for the invitation.
So now you may share your screen.
Yeah. And you see my screen? Yeah, so no problem. Everything is fine. Everything is fine. Yeah. So let's see this one. Is that better? Can you see my screen now? My presentation. So there are some. What do you mean by full screen? What do you? It is in slideshow mode on my display. Okay, so it's not good enough. Try again. Now, better? Is it better now? Now it's fine. Can you repeat? Is it okay now? Super. Okay. So good afternoon, everybody. Thank you very much for the invitation to come here and give a presentation about wind power. I hope you have had a very good conference. I can see it's the last day of your let's say event. So what I'm going to speak with you about today is one of the important renewable technologies, which is wind power, and I will discuss that related to the topic I have been working with for many years, which is power electronics. So, but just before I start, let me just say where I'm based in general. Well, you have your conference down here, right? I'm placed up here in Denmark, so it's about 10 hours flight to Delhi. And in Denmark, we look like this, where I guess what you know is Copenhagen, which is the capital. And I'm coming from a place called Aalborg, which is number 4 big city in Denmark. And in Denmark, in Aalborg, we have a university called Aalborg University. And maybe many of you know Hans Christian Andersen, which is a very famous poet about Denmark. Maybe you're not knowing so much about Aalborg, but the interesting thing with Aalborg University is that we are around 50 years old, and our university is based on the students. They work in teams all the time, so we train them in working in teams. And that means in Aalborg University, we have what we call a problem-based education model. So the students, they work with problems. And that has resulted in that in some of the rankings, Aalborg University come very high out in the disciplines, and where we can talk about, let's say, problem-based learning and also solve problems. This is absolutely in engineering. And that's the reason we are relatively highly ranked in some of the rankings. For example, US News, and in electrical engineering, we are very, very strong. But that's not the main topic of today. Today is about wind power. And first I'll give an overview about wind turbine history and also the evolution in Denmark. We have been for many years a leader, but of course many other countries now are catching up because they are trying to reduce carbon emission. Then I'll talk about what all of us, I guess, we are interested in, the power converters and control. I will discuss some of the trends where, let's say, we look at how we can build. What you really can see here is that this has been taking off in the history from year 2000, where we have around 900 gigawatt, where most of it is hydropower. Now you can see we have much other colors, and solar and wind are really dominating. So in 2022, we have installed around 3,500 gigawatt. That is a little bit expanded here on this diagram, where I have added, let's say, 2023. And what you can see here is that now we have passed 4,000 gigawatt of installed capacity. So I think US, for example, they have 1,000 gigawatt of installed electricity capacity. And what is interesting also to look at here is that in around 2020, hydropower was passed by PV and wind as such. If we look at year by year, what is the, let's say, the annual change, and that means also what is the renewable energy market. And you can see here a dramatic growth from 2001, where maybe 10 gigawatts to close to 500 gigawatt in 2023. The red one is the wind, but you can see that in this case here, what has really taken off in the last years are the PV, because the PV has become extremely cheap to manufacture. However, what I'm discussing here is, of course, related to the wind, and it's interesting to see also how the world has adopted wind, and also have adopted, let's say, what I can call different technologies to produce the electricity. And this one is a little bit old, but however, it's illustrating a little bit a trend which are there in general, where we can say that let's say that the dark ones, they are the fossil fuel based, and the non-dark based, they are the more new energy sources. So here you can see the IEEE member countries in 2017. Where what is of course interesting, seen from our discussions today, who are the most, let's say, who are using most of wind in order to generate the electricity. And this is the light blue, and you can see some countries are really doing a lot. Some have a dark blue. This is hydro but you can also see countries which are really based their energy system on fossil fuel, where you can see the top ones up here. And this is gradually changing, where this part here is becoming less and less. But one of the big light blue parts here, you can see this is Denmark, where wind is covering significantly of the electricity generation in 2017. And let's say that is even much more today. You can also see here, for example, Norway, right? They have a lot of hydro resources, so they are also very renewable based, if we can say so. I'm struggling a little bit. So as you can see, Denmark was very much becoming renewable based and wind based. And let me just illustrate that a little bit by two figures here from 1985 and from 2015, where the dots indicate the generation capacity in Denmark. And what you can see here in 1985, just a few dots. That was big power generation systems based on coal, maybe a little bit natural gas. But then Denmark decided to be much more independent on external energy flow. And that means they decided to distribute a lot more the production and install different capacities in terms of doing electrical power generation. And you can really see that we have been changing from, let's say, centralized production system to become a very decentralized electricity generation production. And you can even see that we have located some dots in the ocean, meaning that we also have installed a lot of offshore wind power capacity. What is also interesting to see is some of the red dots have disappeared. That means that we are moving into a renewable-based system. But you can also see that we have strengthened the connection to our neighbor country, Norway, up here. You can see Sweden, and we have even got a connection down to Germany. So in order to go in that direction, it also demands flexibility in terms of operation of the grid system. Here you can see the electricity generation until 2021 of Denmark. Where are the sources? So you remember the diagram with a few dots, right? In the beginning, this was very coal-based. What then has happened is that we got natural gas, oil as a production, but that is now being phased out. And what is really coming into the electricity production as a source has been the wind. So today, more than 50% of the electricity is generated by wind in the Danish system. Also, waste. Biofuels are playing a role, and gradually solar PV is also coming in. So if I look at the big perspectives in Denmark, solar PV is also going to play a significant role. In terms of turbines, where have we located them? Now we look at the case of Denmark. Here you can see the number of turbines, and here you can see the number of onshore installations, and then you can see the offshore. Now remember, there's a zero here, so it can be a little bit misunderstood. So what we can see here is that most of our turbines, they are really located onshore, while offshore is less. On the other hand, the offshore turbines are larger, so that means the capacity is in average is much higher. So in total, we have more than 6,000 wind turbines installed in our system, and they are generating around 60% of the electricity of today what we are consuming. Here you can see the capacity on offshore and onshore. And again, when we look at numbers, 1/10 of the numbers were offshore, but you can see the capacity here installed in the Danish system. 2.5 gigawatt are offshore and 7 gigawatt are onshore, of course, meaning that the capacity of the wind turbines are much bigger offshore. Here is illustrated where they are installed on the Danish map, and the red ones are the offshore wind farms. So you can see the size: 400 megawatt, 600 megawatt, 200 megawatt. Here we have around 1 gigawatt. And then onshore they are also installed, let's say, a lot of wind turbines. Here's one example how this is realized in practice. If you have not seen it, this is one which was erected, let's say, 10 years ago. And maybe you think, okay, why does it stand like this? But in general, when they are, let's say, designing wind farms like this, there is a big optimization where they look at what is the most, where do the wind come most from, and then try to optimize the location of the wind turbines and reduce, let's say, also the interaction between the wind turbines in terms of how much shadow they will give for the wind which is coming there. So I think here more than 100 turbines where a big optimization is done according to a certain wind profile, which are, let's say, expected and coming from statistics over the many, many years. The wind turbine technology as such is provided by larger players around the world. Well, this goes a little bit up and down depending on where the market is. But this one here is sampled in 2021 where 100 gigawatt was installed. And this one illustrates Vestas as number one, Goldwind, which is a Chinese company, as number two, Siemens Gamesa, which is a Danish, German, Spanish company, and then you can see the rest. But what is also interesting to, let's say, to look at here is the capacities which have been installed both onshore and offshore. And in this context, you can see that some countries, some companies are moving more and more into the offshore or have got orders offshore, while others, they have dominant market onshore. So if we look at the technology seen from a history perspective from 1980 and then up to today, we can say that this has been an amazing development where in the 80s, this was when I was a student, the biggest turbines, they were 50 kilowatt. In 2000, they were 2 megawatt, and everybody was saying, oh, now we have the biggest wind turbine at all. But today we have, and we are seeing turbines in this range of 15 megawatt, even up to 17 megawatt now being sold and raised in the ocean. The big turbines, the very big turbines, we will hardly see onshore because it's very, very difficult to transport them onshore. While offshore, when we can do it by ships and so on, then we can raise them. And then you can ask, okay, here we have the biggest wind turbine on this one here, 15 megawatt, a diameter of 236 meter. Will it ever be larger? And yes, still there are predictions that it will still be larger. And everything is, of course, let's say, system optimization from where we look at the foundations and up to, let's say, the blades and the interconnection to the grid. How can this be optimized seen from a cost perspective? History-wise, I would also emphasize that there have been a technology shift from, in the beginning, we were running fixed speed. The grid was just connected to the generator, and then the generator was running almost at fixed speed because it was an induction generator. But when we scaled up, it became absolutely clear that we cannot do that without having a variable speed, harvest as much energy as possible out of the wind, but also lower the torque pulsations when we have wind gust. So variable speed was absolutely a must. And that could not be done. As we know, we have to have variable frequency, variable voltage in order to be successful in that respect. So that means power electronics really do active generator control, but it's also ensuring that the grid interface become much better, and the grid interface can really control on demand what we intend to do. So the colors here are indicating how much power electronics is applied on the technology, and you can see in the beginning very little, then maybe around 2000, the double-fed induction generator system came, and now I would say a lot of power electronics is interfaced between the generator and the grid in order to have the best solution. In respect to, let's say, cost of wind energy and compared with others, this is something which is moving all the time. But here is one sample for a certain year. This is some years ago, but some years ago, comparing onshore wind, offshore wind, because these are the topics today, there is no doubt that the offshore wind to a certain degree was more expensive, and it is still more expensive because of different things. One is, of course, maintenance. A second is it costs more to raise them. On the other hand, we can also say the power available has a much higher, let's say, availability compared with the onshore wind, because we can much better predict the wind. So there are also advantages, even though the technology is a little bit more expensive. And then you can see the other technologies also shown here, which I would say is something which are moving all the time. I would say today there is no doubt that the non-tracking PV is very, very cheap compared with other technologies. So now the conference, I'm sure, is also interested, let's say, in the how do we do the things in terms of wind turbines. And what I can say is that there is not one system which fits for all technologies. If we look at the companies here, manufacturers, you can see by blue which generators have been used, and their induction generator, either full-scale or full-scale fed or double-fed induction generator is used, or the synchronous generator is applied, which can either be with permanent magnets or with wounded rotor. So here you can see the, let's say, the different providers of technology. So, for example, Vestas, they both have, let's say, double-fed induction generator system and synchronous generator. And if they do that, they have to have they have to operate with different kinds of converters. One is what we call a partial scale converter, another one is full scale. And here you can see the power range of the different systems. So there is not just one which solves all things. And here are the concepts. One is the double-fed induction generator system, which is illustrated to the top here, where, let's say, the stator is connected to the grid, and the rotor is connected to an AC to DC and DC to AC converter, where the slip power is then controlled by this AC to DC and DC to AC converter. The beautiful thing of this technology is that this part here, the power electronics, only have to be around 30% of the total system, while if we take the other situation where we have a full-scale power converter system, illustrated here, where we have synchronous generator or induction generator, where we have to deal with the power full here, and we have to deal with the power full here. Absolutely, this is more advantages. But the disadvantages is seen from a control perspective, that when we have something happening on the grid, then we will also see it directly on the stator of the generator. While down here, if something happens at the grid, we will be able to, thanks to the configuration here, to decouple the two systems. So if something happens at the generator here, we can make it so the grid is not seeing. If something happens at the grid, we can make it so that the generator is not seeing anything. And that is, of course, more easy to handle in terms of a whole wind turbine. But on the other hand, of course, the power level of the power electronics and the power conversion, we have to do that twice full. And here are, let's say, some features of the generators I showed for you before. So there was two fundamentally, but we have the cage rotor induction generator. Here we need, let's say, a full power converter. We have the permanent magnet synchronous generator. Here we also need a full-scale power converter. And we have the wound rotor induction generator. This is double fed. Here you can see what is, let's say, the capability, and then we have the DC excited synchronous generator where we have the capability. And you can see there are different, let's say, advantages and disadvantages in terms of how to handle faults and also the reactive power capability which is needed to control the voltage. And there are also some, let's say, solutions in terms of gearbox, without gearbox, with one-stage gearbox, with two-stage gearbox, and so on. And the companies have different solutions. Seen from a control perspective of dealing with the system, let me also illustrate for you how this fundamentally is done. Here to the left, we have the turbine with the generator. To the right, we have the grid, the point of common coupling. And then I have a generic system here, which of course have a transformer where typically we go, let's say, from 690 volt AC to 33 or 66 kilovolt at the other side. So the way we do it is that we have a very fast controller controlling the current both to the generator and to the grid. Also some grid synchronization, maybe running at 20 kilohertz with fast loops. Then we have a next level of control where we control the power. We can support the grid, but we are also able to optimize the energy harvesting from the turbine, as well as we can limit the power when it's operating. A little bit lower, let's say, dynamics in that respect. And then there are a lot of new features which are interesting to have, like inertia emulation, energy storage, black start, and so on, where I would say that they run with a little bit lower, let's say, bandwidth in terms of serving its purpose. But there's a hierarchical control structure which has been applied for many years, and each converter has, let's say, very fast control loops in order to protect it, in order to serve its function. So the converters we are applying are, let's say, gradually, let's say, changing, but there's no doubt that the absolute main converter topologies are operating below 690 volt. And the reason for that is that then we have one kind of, let's say, security protection system of it. If it enters into medium voltage, then different features are needed in order to have a safe system. So what is very often used is a two-level voltage source converter with filters, as you can see here. So we can control the generator and we can control to the grid. In the case that the generator is a system where there are a back EMF and that's the permanent magnet synchronous generator or wounded rotor synchronous generator, then voltage is generated here. Then we don't necessarily need to have an active converter to the generator side, but we need to have an active converter to the grid side. But the power is high, so we cannot just do it with one converter. So we built it in stacks, like you can see illustrated here. Here's maybe a stack of 2 megawatt. And then in order to do 10 megawatt, we put 5 of them in parallel, like illustrated here. This gives redundancy, right? If one fails, we can still operate. However, in order to have high redundancy, there have also been a solution on the market where we have a multi-winding generator, for example, 9 windings instead of 3 windings. And then each converter has connection to three phases, of course. And in that way, we have double redundancy in the system. And it is seen in some solutions today. However, when we move up in a very big power, 10 megawatt and above, it's natural to think about, let's say, multi-level converter topologies and also higher voltages at this stage here, maybe 3 kilovolt, 3.3 kilovolt or something like that. And we are seeing that, and there, in that case, the 3-level neutral point clamp converter is of interest. However, it's a natural thing to think wider. So what I have discussed a little bit is topology like this, right? We have multiple converters in parallel, right? And then we have the collection grid. Also, the medium voltage turbine is illustrated here, for example, 3.3 kilovolt AC. And then we go up to, let's say, 33 or 66 kilovolt AC. But it could be interesting to think about, and there are people looking at that, let's say more high voltage generators, and then also a high voltage converter, where, for example, the voltage is 12 to 66 kilovolt AC, and then we are avoiding this 50 hertz transformer or 60 hertz transformer. And there are a lot of advantages, but there are also challenges in terms of insulation system, short circuit protection, and in general safety in, let's say, in the generator system. You saw the photo where we have many turbines, and of course, we put them together to, let's say, aggregate a wind farm to be a big synchronous generator, 400 megawatt or larger. And what we can do there for the double-fed induction generator systems or for the full-scale converter system is, of course, to have an AC grid from offshore to shore. That is illustrated here. However, if the distance become long, then, okay, we have an AC, let's say, collection of the power, but then we go from AC to DC, and then transmit the power by DC. And this is also solutions already seen. But what could be obvious when we look at, let's say, how many times we convert the power was to have, let's say, a medium voltage DC grid and then go from DC to DC up to high voltage. And in that way, save some conversion status like illustrated here, and also transformers. We have not seen that yet, but it's obvious seen from, let's say, just a block diagram perspective. And then, of course, we have to do, let's say, this kind of solid state transformer or DC-DC transformer, which is able to handle many megawatt if we have a wind farm of hundreds of megawatt. But that's on, let's say, on the, let's say, studies. If we have an AC system, which is illustrated here, you have the wind turbines here, cables, we collect the power, we have a high voltage AC cable. Then we know, because we have an AC cable in the ocean, that reactive power is, let's say, is become generated. And in order to have a good quality of the power at the PCC, which is at the transmission system, we typically install also STATCOMs to compensate for that. And there are different, let's say, ways of doing the STATCOM, and there are also different providers in order to do it. But the STATCOM serves to compensate for the reactive power, but of course it's also supporting the system in terms of voltage stability, fault right-through capability, and it can also compensate for potential harmonics, which are seen in the system here. Okay, let me end my presentation for you this afternoon on, let's say, what are the more wider perspectives. And for years, energy island have been discussed as some new ways of thinking in terms of, at least seen from a European perspective, because the capacity, the potential of energy and energy harvesting in the ocean in the northern Europe is, let's say, placed on the ocean. And this is, for example, illustrated here that we have a lot of energy resources. Here's Denmark, like Germany, Norway, Sweden. So out here, we have a lot of energy potential. We also have a lot of energy potential here, and the depth is not super high. So some plans have been highlighted by, for example, the Danish government that, for example, we can build capacity here of 1 to 4 gigawatt, and we can also build capacity here 1 to 4 gigawatt, but there are much more potential if we look at how much area we have available. So how to do this, and also in that context, there has been, let's say, a discussion on, okay, we need electricity, but we also are not able to decarbonize all sectors without going through, let's say, a hydrogen path and have a high energy density fuel to do some processes. For example, a fuel for airplanes. So if we place a lot of capacity, for example, in the North Sea, like you saw before here, how should we do this? One way to do this in a way where fundamentally it could be cheaper was to build an island where then we have multiple turbines, farms, which are feeding power into those islands. And then the power here is handled with a combination of load, where this could be hydrogen production, or it could also be other processing, or it could be, let's say, connection to shore to different countries. And here have been some discussions on what are the most interesting way to do it. And in that context also, okay, if we do electrolyzing here, we have a hydrogen being produced. Why not do a hydrogen pipeline? Because there we can have much more capacity compared with just doing electric, let's say, installation of 4 gigawatt, 2 gigawatt or something like that. Doing a pipeline gives a capacity which is much higher. If you look at the gas pipelines, they have a way high power capacity. So for the moment, this is being explored in the Danish system. So to the east side of Denmark, we are exploring and planning to raise, let's say, the first somehow energy island, where we connected also to HVDC lines, one going to Denmark and one going to Germany. And the fundamental idea there is that we have one wind farm of 1 gigawatt. We have another wind farm of 2 gigawatt. They can be connected, they can be disconnected. And then we are looking at, okay, how should it be done? So there is bipolar HVDC on both systems, and then they can be connected and in a configuration like illustrated here, with some terminal stations here, and also some terminal stations here, and then a DC cable. But of course, what is interesting to discuss here, how can we make such system, which can be huge? How can we make it resilient? How can we make it stable? And of course, last but not least, how can it be more economical? And different things can be, let's say, explored. For example, one is, should such an energy island, should that have the same grid codes like which exist onshore, or can we relax on the grid codes and in that way maybe save some, let's say, hardware hardware specifications on the wind turbines? And another thing which is interesting also to discuss is, when we have those systems on the island, should it be AC, or as an AC hub on the system, or should it be a DC hub we are basing the system on? And dependent on how we do this, then of course, let's say the cabling and the other systems, for example, the electrolyzer, will be, let's say, be different. So that was just to, let's say, to put a little bit thoughts into that. We are thinking big in general about wind power. We are thinking very big in terms of having aggregated a large amount of power in order to control the power grid, but also thinking of how can we, let's say, optimize the connection to the shore in all aspects, so the levelized cost of energy is not becoming too high. So let me just highlight a few things which are future trends in wind turbines. One is floating wind turbines in order to save money for the foundations. Another one is obvious, and that is, of course, how can we apply energy storage and improve the performance of wind farms or the wind turbines? How do we transport the electricity from A to B? HVDC is absolutely the technology to do, but what are the best solutions in that respect? Also, when the wind turbines are going up in power, then we need high power converter topologies, as well as when we look at HVDC terminals, stations, how can we go up from 2 gigawatt, 3 gigawatt, 4 gigawatt in a good way? Grid codes are absolutely on the discussion whether the turbine should be operating grid forming, grid following, or something in between. And that involves, of course, also improvement of the control technology. So this is absolutely a case where it's really not just, let's say, to optimize the technology, but it's really also to be in the front edge in terms of, let's say, coming up with new innovations for the technology in order to stay competitive. That I recently, some of the thoughts we published in a Nature paper, in Nature Review, and if you are interested, you can get a copy of that one and maybe study some of the thoughts there. So, summary: wind power has really developed in a country like Denmark, and I think 60% of all electricity is coming from wind today. So we are one of the leading countries, even though we are a small country compared to yours. We are relatively a leading country in this technology. In some locations, onshore wind is somehow saturated, but then offshore is a way to look at other potential. Energy islands are being discussed in the Danish, but also in the European context. I demonstrated that for you, and the first study is about 3-4, but expanded to be much bigger on the long run. But I'm sure that by my presentation here today, you can see that we can really not, let's say, realize all those things without power electronics. So this is really a key in order to be successful for the technology. So with that, thank you very much for your attention this afternoon, and I'll be happy to answer questions you might have. So thank you very much. Hello.
Sir, is anyone having any query?
Anybody having any query? Sir, can you hear me?
Yeah, I can hear you. Yes.
Myself, Pradeep Dashari. I am from Electrical Department.
Sorry, can I for him?
हाँ.
अच्छा वीडियो है.
Can you hear me, sir?
Sorry.
Are you audible?
Yeah, I can hear you. Yeah, I can hear you.
Whatever you want, I have seen. Islanding and using AI. What scope of work we can do over there by using means if you use power this component on the islanding and AI, can you mix all those things? Is there a scope of work?
Yeah, maybe you can repeat that. Can you repeat the question? Is it about islanding? Is about islanding, right?
Just a minute. So I'm coming.
Okay.
Can you hear me, sir?
Yeah, that's better. Much
Yeah,
better.
fine. So I want to ask actually that in islanding, can we incorporate some power harness component, and can you mix the work with the AI islanding and power harness component?
As you want, when you mean islanding, that means they are disconnected from the grid or what?
Yeah, say some malfunction is happening. If some malfunction is happening in the grid or maybe in line, so at that time islanding is required. And whatever I understood that we are going to use AI over there. So I want to ask that is there any role for power harness component to play on that scenario?
Sure, absolutely. Absolutely. When we have those situations, we need very advanced. We need advanced control strategies, and those control strategies can also be based on, let's say, some learning algorithms in order to do the best decision for the specific, let's say, situation. So we could easily imagine that, for example, AI is applicable in such kind of control event.
No, sir, I'm asking about, sir, the timing of reaction of our protection system over there, because
yeah,
what should be the range of timing at that time?
Okay, if it goes into island operation, what happens is all wind turbines, they have a protection system where they can dissipate the power in the DC, also in the DC link. So if they cannot get rid of the power, for example, if the voltage become zero at the grid, then they can dissipate for a short while the power in the turbine itself, and then let's say shut down, let's say the wind turbines, so they are not operating anymore. So this is standard to put that into wind turbines today.
Okay, sir. Thank you.
Yeah, you have to think the worst case, and the worst case is really that you cannot get rid of the power and you're producing power full power, and in that case you have to have a place where you can get the power down to zero. And you cannot do it. You cannot do it in 10 milliseconds because it's a mechanical system. So it takes time. It takes time because it's a very big construction.
Anyone having any more query? I think, sir, we are up for the questions. Thank you, Professor, for such an enlightening and engaging lecture. We truly appreciate your time and dedication. On behalf of everyone here, thank you once again for sharing your wisdom with us. Thank you, sir. Hope we will again meet.
Yeah, thank you. Have a nice conference.
Good afternoon, good, Doctor. Hi, I'm sorry, Doctor Bikaram Das. There was a communication error. Now it's okay. Yeah, I'm fine and hope you are well and fine in India. In Yeah. Mhm. Okay. And let me know my audio and my video is visible to you all. Okay, thank you. Thank you. Thank you very much. Thanks a lot.
Sir,
Our next expert speaker is Sanjeevi Kumar Padmanabhan, who received a PhD degree in electrical engineering from the University of Bologna, Italy. He is a full professor in electrical power engineering at the Department of Electrical Engineering, Information Technology and Cybernetics at the University of Southeastern Norway. S. Padmanabhan has authored over 750 scientific papers and received the Best Paper Cum Most Excellent Research Paper Award from IEEE SILCON, IEEE CNET, IEEE EECSI, IEEE SENCON, and the 5 Best Paper Awards from Sponsored Lecture Notes in Electrical Engineering Springer Board. He is a fellow member of Institution of Engineering India and received a Lifetime Achievement Award from Marquis Who Is Who, USA 2017 for contributing to power electronics and renewable energy research. He is listed among the world's top 2 scientists by Stanford University, USA. Over to you, sir. You can start your session.
Thank you very much for inviting for this IEEE conference for my keynote speech. Could you please confirm my audio and the slides are visible to you?
sir, can you present your screen? Sir, your audio video is visible, but your screen is not visible.
I think you have to give me access because as a host, you have to give me the permission to share my screen.
Sir, I have stopped presented. Sir, now you share your screen, sir.
Could you see my screen now?
Yes, sir. Yes, sir. Now it's visible.
Thank you very much. So, very good afternoon to all participants and organizer of this IEEE conference, and thanks for inviting me. Today, I'd like to present a topic which is based on our research activities carried out for several years in electronics and renewable energy system, which is AI-inspired renewable energy systems based on electronics applications. So today about renewable energy, which is all the countries are focused towards 2050 to have 100% fossil-free energy systems. Now, currently, if you look at the most CO2 emissions are transportation, particularly from roadways, airspace, and marine technology. About Norway, which is around 2021, about 82% are become EV, electric vehicles. So there is a sustainable developments towards electric vehicle with renewable energy technologies, and the goal is around between 20 to 35 to have 78% reduction, and that is a goal of most of the countries across the globe, and we are also working towards that. For these all applications, the most important thing is the power generation. To reduce the fossil fuels to more renewable energy systems, we need more power electronics innovations. And when power electronics innovation comes, we need to integrate more information technologies and communication aspects with respect to microgrids, smart grids, and integrating renewable energy to grid. So these requires Internet of Thinking, big data, cloud computing, and machine learning algorithms, so that the power become more flexible for transmission and distribution to reach the consumers. The consumers can be EV, electric vehicles, or grid, etc. As we know about power generation systems, we have fossil fuels as well as the renewable energy systems are get connected to the transmission towers and transmission lines and distribution networks, where it is not absolutely a green energy. It has a several percentage of fossil, but in no way 85 to 90% are renewable energy systems because they are powered from hydropower plant. So in this case, in the future, we are going to have more than 250 million batteries. Small storage technology is going to be revolved around the world, and these small energies can pump the power to the grid as a green energy. So now currently we are having grid to home communications. In the future, we will have grid to vehicle to grid communication through the DC chargers, and all the residential homes will be connecting with the grids, and commercial aspects of large industries and malls will also be connected to the grid by using aggregator, where we have the freedom to switch the power supply between renewables. For example, if wind is giving more cheaper, we can shift to wind. If hydro is giving more cheaper, we can shift to hydro. Or if the photovoltaic is giving more cheaper, we can shift between the different power supply. And of course, each batteries can pump the power to the grid and make as a entrepreneur benefits. So each consumer of electric vehicles with the small batteries, we can earn money in the future. For all these aspects, we need to integrate artificial intelligences and power electronics converters, both in the charging unit as well as in the powertrains of electric vehicles. Apart from batteries, batteries are having limited lifespan, not more than 8 years, and the durability and reliability are restricted with the batteries for high power applications. Sorry, in these aspects, in order to replace the fossil fuels, particularly crude oils for diesels or petrol, fuel cell is an alternative technologies where we have a low power, minimum 50 watts to maximum less than 100 megawatts, and the temperature range lies between minus 20 degrees centigrade to greater than 80 degrees centigrade, which shows a large reliability of fuel cells adaptable for different power supplies and the environmental conditions. Apart from that, that can be adapted for a small electric vehicle to a large electric vehicle. For example, if I'm going to use a reformed methanol fuel cell, it can be adapted for a temperature between 80 to 300 degrees centigrade, and it can be used between the temperature with the power minimum 10 milliwatt to the maximum 1 kilowatt, and it can be adapted for large electric vehicles. So buses, trucks, big cars, ships, etc. There is an option for using reformed methanol fuel cells, but the cost of generating hydrogen is very expensive. One of the fuel for the fuel cells along with the oxygen. So the technologies are growing up with optimizing these renewable fuel cells for optimized cost in the future. So the potential candidate for replacing fuel cell is going to replace the fossil fuel is going to be the fuel cells. About typical applications in powertrain, particularly on electric vehicles, we have a combination of fuel cell based batteries. So you have a fuel cell storage cartridge for storing the hydrogen, which is given to the fuel reformer, then to the fuel cells, which converts this hydrogen into DC power supply. But the power supply which is generated from the fuel cell are not sufficient enough to drive your electric vehicle, because it's a large power system. We need DC converters which pump the power to a higher level, then back to a DC to AC converter, which converts to AC power supply to drive your motors. Apart from that, we have electric storage devices for the power supplies or batteries. Currently, lithium ion batteries are highly used, but as you know, the lifetime is limited to 8 years, and they are very expensive. And these batteries can be compensated by using parallelly ultra capacitors, because ultra capacitors can be store energy by using AC or DC, and there is no limitation for state of the charge, and it can be more reliable, and there is no deterioration. So these are aspects. Supercapacitors and ultra capacitors are going to be an alternative for batteries in order to reduce the cost. So the complete power system going to have a hybrid model which has a fuel cell, power electronics converters, batteries, and ultra capacitors, both used for medium voltage and high voltage requirement of electric vehicles. Please note the efficiency provided by fuel cell is only 60%. So we have to use it very effectively. The power generation available from the fuel cell by using power electronics converters, which can go above 80%. If you look at a very large electric vehicle, we have to need a DC microgrid within the vehicle. On your right hand side, we have a batteries which goes up to 700 volts, battery controllers, fuel cells which is having high power capacities in megawatts, which can be connected to your electronics converters of DC to DC to couple to the common point of coupling on a DC microgrid. On aspects of application, the DC power will be converted into AC, because we have AC loads on your electric vehicles of large transportation system which has around 20 kilowatts. Then this DC power has to be converted into AC to drive the motors. Then the luxurious needs within the electric vehicle can be high voltage as well as low voltage, which can go up to 25 kilowatts. What is the luxurious needs? Lighting, air conditioning, and of course protection units, etc., which is available in large vehicles or small vehicles. So in the future, it's going to be electronics as well as all hybrid renewable energy system going to be the powertrain of our vehicles. In these aspects, we have developed many electronics converters from our research group for many years, and particularly a model we call it as a triple mode active passive parallel interconnected converters. This is the converters we already done it, and we have of course made it as a pattern for commercial aspects. So if you look at closely the converter module, it has a DC source, and if you have only one bridge, it's a standard half bridge converter, and one of the MOSFET has been replaced by inductor. Then we introduce a new leg which is having one MOSFET in series with the inductor and a parallel combination of capacitor, and there is a current controlled diodes. So what is that? You energize the inductor VL. When the device S1 is closed, we energize the inductor L1. And when the devices are open, all the energy are transferred to the capacitors. We get a large energy storage from the inductors will be delivered to the load side boost converter, which is a standard boost converter, and you are able to produce a very high voltage. So in these aspects, based on your high voltage requirement of the vehicle, we can able to increase the legs to n times in a very compact way. With a simplified MOSFETs are used to control along with the inductors and capacitors. And these application can be pertained to a DC microgrid where we have 400 volts or 800 volts or 1200 volts above if it is required as per the infrastructure requirement. On your right hand power can be AC, so it can be converted into DC by two stages, AC to DC, DC to AC, back to AC to DC by using AC to DC converters. Then we have existing transmission lines. We have an existing transmission line which is controlled by AC voltage regulator, coupled again to AC to DC converters. Then we have a battery banks. In the battery banks, we have stored energies from the excessive power available from the wind or transmission line will be stored here, and we come back to the grid by using AC to DC converters and back from AC to DC to the common grid of coupling. So power electronics converters are applied in various power supplies. On the part of the applications, we can use DC-DC converters for charging the electric vehicles. As I said, the stored energy in the small battery vehicle can pump back again to the microgrid. So we get a power back to the microgrid in a bidirectional way from an electric vehicle. So grid to vehicle and vehicle to grid communication. And of course, we can use a lot of photovoltaic systems. These photovoltaic systems are connected to the grid by using DC-DC converters. DC to DC converters, which can store the energy from the photovoltaic back to the batteries or to the common grid, so that we have a flexible power transmission. Most of our applications are focused towards DC applications. We have chargers, batteries, laptops, etc. All these are connected to a DC-DC compact converters to provide lossless power generations. Once we design the converters, we are testing the efficiency at a low power scale between 100 to 500 watts capacity. At 100 watts capacity, the efficiency is around 94 simulation modules, as it goes near to 97% when we are reaching 500 watts. But in the real time, the efficiency comes down to near to 92.3 or 4% at 100 watts to the maximum 93.7 watts or 8 watts at the rated power of 500. The reason is, in real time, we have switching losses, conduction losses, and passive and conductive losses, etc. due to both the active devices and passive devices and cables and processes. You are unable to get as expected numerical model efficiencies. Of course, the efficiency is not nearing to 98% or 99% because we have tried these modules in laboratory scale, which is around 500 watts. About dynamic testings is very important in any power electronics converters which are applied in electric vehicle charging units or to the powertrain within the electric vehicles. We have to charge and use the DC-DC converters for delivering the proper power. So in these aspects, we are testing various power electronics converters what we have developed from the laboratory module by using advanced FPGA solutions, using components available within the laboratory modules from the low-cost prototype like capacitors, which are readily available in the markets, FPGA-based controllers. We are testing at different dynamic conditions. This is an example where we can able to show you when the voltage is fixed. You can have a look at battery voltage, say between 24 volt to 48 volt is fixed, very constant in the dynamic modeling of testing in real environment. And we regulated the output voltage for various environmental conditions. For example, if you consider an electric vehicle, it can go for a low speed to high speed, then back to a low speed, and continuous braking is applied. And these brakes will generate power back to the batteries and fuel cells that has to be protected. So this is very important analysis where we look all the power quality analysis and various regulations. All the cases, the input voltage is maintained very constant regulations, and the current is almost constant as per the requirement of the input side, which is having more renewables, hydrogens, etc., electrolyzers, whereas the load current is regulated based on the load requirement. All the cases, we are looking very carefully the current through the inductor, which is connected to the electrolyzers, and all the renewables which is used in the applications. So all these currents are very smooth. You can have a look. We call it as a ripple factor or distortion factors, which is available in the DC power of the current. They are regulated less than 1% is our goal, because to keep a high quality profile of the power supplies. So all the cases we are getting as per the standards. It's very limited distortions, ripple content, and able to produce a high quality waveforms. And this is already patented in US in 2021 for commercial aspects. And in detail, I like to show you some more on the characteristics. In numerical model, we are trying to keep near to 40 volts, and the current through the index are periodic, and they have a unique peaks. And about the output current is stable, and output voltage is also very stable. And we are comparing at two different levels of aspects of applications, both in numerical model and simulation modules. And of course, here we have a simulation module. We are showing all the capacitor voltage, because capacitor voltage is very sensitive. A small spikes or deviation in the current and the voltage can easily spoil your capacitor for open circuits or short circuits. That's the real challenge with capacitors. But in our module, what we design appropriately by using the controllers and prototype model of the converters, proper selections, all these capacitors are regulating required voltages at their levels, and of course the inductors. In real, it's most important, all what we study in numerical model must match in the real time. We are trying to keep the voltages like a battery model, say 24 volt to 48 volt in the real time. Then we are looking at the currents. So the inductors are very smooth, periodic, and of course the output voltage and output current. And the most important, as I said, the reliability of the capacitors are very important, because there is separate research is going on reliability of capacitor and enhancing its capacity. We are having a very smooth regulation of voltages in both the capacitors, and there is no any spikes which can easily spoil the capacitors for its long time applications. And very smooth the periodic ripples are seen, and of course the currents through the inductors as well as through the output are as expected. Apart from these converters, we also develop many power electronics converters which are focused towards high voltage applications, particularly on integrating two levels of common point of coupling. One is on the renewable energy sides, maybe between 24 fuel cell stacks, photovoltaics, and batteries. And we need an intermediate power electronics converter to match a high voltage side, which goes for 400 volt to 800 volt or 1200 volts, which can use for charging the electric vehicles, DC microgrid systems, DC home applications, and DC AC microgrid, which is an existing systems. We can pump the power. So all the cases, we need a strong power electronics converter which can balance the power supply as well as the long time reliabilities. So in this case, we introduced tri-state power electronics converters. We have three MOSFETs, and they are triggered at three different levels. That's why we call it as a tri-state power electronics converter, DC to DC converter. If you look at the configuration, this is a standard full bridge converter. In the full bridge converter, we replace two MOSFETs by inductors. So when the device is closed X, you energize X inductor. When you close the MOSFET Y, we energize the inductor LY. When the devices are open, we are delivering these power back to the capacitors CX and CY, and these power will be added up, and we are delivering to the load side boost converters. And we introduce the diodes, the DY, DZ and DX to make the current flow always from source to the load side and not in the reverse direction, so that all the renewables which are connected on the input side are well protected. And about analysis, we always look at the utilization factor or duty cycle from 10% to 60%. We are trying to use all these power only maximum 60%, and we are getting a gain which is around 42, which is pretty good when compared to the existing solutions which is available in the literature or in the markets. We are very high at our own levels. Once the converter is designed, the gain factors are analyzed based on theoretical backgrounds. I didn't show you a theoretical equation here because of the time constraint. Then we look at the last modules. All the MOSFETs, the three MOSFETs generates around 17 to 16% losses. Diodes generates between 5.2 to 4.8 percentage of losses, and 6% for the capacitors, and 9% for almost all the inductors. So we have a complete scenario of losses generated by the each active and passive components. Then we have put it into the real-time applications for our requirement around 400 volts. Of course, it can go for 800 on the load parameters or the design requirement. So we are trying to keep the voltage around 400. It looks an average 400. It's not true due to the various switching losses, conduction losses, passive and active component losses. This can come around the 393.4 something volt required. Then this is the voltage across the diode, which shows forward bias condition, and voltage across the MOSFETs, which is pumped back to 185 volt, but the input is only 24 to 48 volt regulations. And these are the currents through the inductors that are very important. You can have a look. The current, this is directly connected to the source, so we are looking very closely the current, and they are very periodic, and there is no any abrupt operations, so that all these renewables or load side integration can be affected. So we ensure the reliabilities, and any sort of distortion creates the power quality issues. And about, as I said, always very important, the regulations, because the regulation plays a critical role in application of electronics converters in real world. So we try to develop a compact electronics converter. You can have a look. It's very small in size. You can have an idea how it looks. It's like 10 centimeters versus 20 centimeters sizes. We are making very compact structure by using available passive diodes and active components and passive components available in the market at cheaper price. And if there is any fault occurs, we can readily replace the components, and it's cheaper. And it's controlled by advanced FPGA solutions for closed loop operations, and we are regulating the power at different scales. So the output power is regulated from a maximum to a minimum value. You can have a look, because the speed can vary from maximum to minimum, or we apply a brake. Several conditions, these regulations can happen in your electric vehicle. And your input voltage is always constant with all the regulations, and the input current is regulated based on the load requirement. And of course, the load current regulated according to the load profile set. So here, as I said, the voltage cannot be 400 volt because of the various losses. We are getting around 395.2 volts, and we regulated this voltage from the maximum value to a set minimum value of 206 volts. So you can have a look. All the case, the voltage is regulated periodically, very smooth spectrum without any huge oscillations. All the cases, the input batteries or photovoltaics or renewables which are connected doesn't have any oscillations. It looks very smooth with the input voltage regulations. And these are the currents to the inductors, which varied from a maximum of 16.59 amperes towards 4.6 amperes. All the cases, there are no huge spikes which can easily damage the components. And the load current are shown here, which varies from 1.22 ampere towards 0.64 ampere in a very periodic way. How we are regulating all these values? By controlling the three devices. In the beginning, I told you we have three MOSFETs, and they are regulated at different levels. That's why we call it as a tri-step electronics converter. The first two devices are conducting 50% and 35%, so we are able to get 395.2 volt. When the devices are conducting around 35% and 35%, it means we use only 35% power of the renewables. Then it goes to 206 volts. Apart from that, we also develop many power electronics converters which are based on sophisticated, simplified approach. If you had read Nate Morgan or any power electronics book, you maybe heard about the term SEPIC converters. They are widely used in real-time applications. But SEPIC converters are having a restriction on the output voltage and power transfer and losses. So we modified that and brought a new configurations, which we call it as a modified or a new gain new SEPIC converters. Here we introduced the new inductors, which is LX and LZ, and made new components like C1 and D1 and D2, so that this configuration become a novel configurations. And the idea is to have one MOSFETs. When the MOSFET is closed, the energized inductor voltages LX and LY will be done. When the device is open, these energies will be transferred to C1 and C2, and the C1 and C2 voltages will be added up and delivered to the load side capacitor C3, which is a boost converter. So we get a very high power that can be verified from here with respect to the regulation of the load. We regulated the output power from 60 to 100 percentage. So at 60 percentage, we get an efficiency of 89.1 percentage. When we go near to 100 watts, we got 91.4 percentage. So here again, we are not getting a very high efficiency near to 98 or 99 percentage, because we are working with low power module for a high power converter. That's the one reason for the safety aspects, but it's pretty good. At 100 watts, we are getting 91.4 percentage. And what are the losses? The MOSFET, which is the critical losses in this configuration, which is around 47 percentage, and the diodes, which is between 13 to 12 percentage, inductors 10 percentage, and of course the LY will provide 1 percentage greater, and C1 is around 5 percentage capacitors, and the combination of LZ, C2 and C3, which is around 0.4 percentage. So we have the complete spectrum of the losses and passive components. And how we can improve this efficiency? If we increase the power at high level, obviously this goes to 98 percentage. And under this testing modules, we took it as a battery module by doing a regulation of 24 volts. So input is kept around 24, and the load current is regulated for 0.51 ampere. And the current through the inductors is very important, as I said from the beginning. They are propagating with a constant oscillation or ripple. So the ripple factor is well observable with a minimum level. And this is very good for the renewables which are connected in the systems. And output to 172 from 24 volts. So this is a continuous conduction of mode or linear mode of operation. But in electric vehicles or electronics, components are not linear. They are highly non-linear in characteristics, particularly the inductors and capacitors. So in order to understand the non-linear behavior, we operated in a DCM. In electronics, we call it as a discontinuous mode of operation at a very high frequency. You can able to see the diode voltages are shifted between two levels, 92 and 152 volts, and the currents through the inductors are jumping between the peaks and zeros in a periodic intervals. This ensures the system is highly nonlinear. Even during this discontinuous mode of operation, we are able to track 92 volts from a battery source of 24, which is pretty good for the applications in real time. So we developed many electronics converters from our labs, which has its own unique future. We have developed switch to capacitor based power electronics converters that are used for high power high reliabilities, cheaper cost, and high efficiency, smaller size, modular. And the disadvantage is the poor regulations because of the large capacitors are used. That's why we call it as a switched capacitor based converter. And this is only applicable for low duty vehicle and low power application. We also developed switched inductor based converter family. They are very high reliable because we are not using any capacitors. Very few capacitors are used, one or two, and the cost is very high because we need more inductor, and the efficiency is good, and they have a very good ratio for transferring the high level to low voltage conversions because of using the inductors. But the disadvantage, we use a lot of inductors, so the performance of high power is restricted. So we use only for low power applications in electric vehicle. And we also developed the fourth one, which is the multi-level converters, the average reliability, high cost, and very high efficiency. It can be advantageous to have balanced extendable structure because of a low number of switches we use, like MOSFETs or IGBTs. Disadvantage, we use more capacitors and diodes, and this can be applicable for high duty vehicles. Also, we develop a family on XY power electronics converters, which are having high reliability, average cost, and high efficiency. And the most important thing is we use only one MOSFETs or one IGBTs. I showed you an example where I used only one MOSFETs and IGBTs, where this can be easily extendable structure because compactness of passive components. But the disadvantage is that we use more diodes, and it can create discontinuous current at the input. And this is applicable for low voltage as well as high duty vehicles. And we are comparing in the middle guy, which is a popular solution, resonant converters or transformer or coupled inductor based converters, which has an average reliability. Cost is very high, efficiency is very high. A disadvantage advantage is that we are using stop switching for voltage and current. By using high frequency transformer, it is tunable to change the power at different scales. But the disadvantage is bulky because we use these high frequency converters, and they produce a lot of magnetic coupling losses and magnetic losses, and only applicable for high power application. If you look at the scenario, what we developed 1, 2, 4, and 5, we have a comparison with the standard solution. Based on the application, we can use a low power application based switched capacitor, switched inductor, or high power application multi-level converter at lower cost when compared to the standard solution. And of course, under faulty condition, if you find an optimal solution between high power and low power application, from our investigation, XY power electronics converters can be highly used because they have a bridge between low power and high power requirements within the electric vehicle. Apart from AC, DC-DC converters, AC converters also play a critical role in transportation application. For example, this is the most advanced 6-phase converters, where you have 6-phase induction drives or synchronous drives, which are powered from 4 different AC to DC converters, which converts DC power to AC. We can have batteries, we can have photovoltaic systems, we can have fuel cells, or we can have any other power supplies. Supercapacitors can be integrated to these systems for high power applications. What is a key feature? If you look at the phase voltages which is going to be generated across the windings, will be having 9 level like a multi-level inverters, and the current and the voltages which are going to be more sinusoidal with reduced harmonics. You can have a look how the voltages are having more sinusoidal characteristics like a 9 level inverter. And if you look at your line voltages, you can able to have 5 levels. But if you have a 2-level converters, this will be between 0 and plus VDC. But since the configuration has been upgraded, we have 3 levels, clear spectrum of 3-level multi-level operation within the line voltage. These ensures high quality waveforms, smooth propulsion of your drive, torque, speed, and reduced harmonics. Once we design power electronics converters, always the application is focused towards controlling with artificial intelligence algorithms. Here I like to show you a basic version what we developed with V/F control for a centrifugal pump applications, where we have hybrid renewable energy from wind turbine and photovoltaic systems. That is connected from the wind turbine through permanent magnet synchronous machine is connected to the rectifier, which converts AC to DC. Then we develop a new cut converters, a DC to DC high power converter, which is controlled by ABC MPPT algorithm. So ABC is the artificial intelligence systems. Artificial B colony algorithms be introduced, and it is controlling this power electronics converter. And photovoltaic system is again back controlled by the cut converter what we developed along with the battery. So if you have an excessive energy, it can be stored in the battery and pump back into the inverters to drive the induction drives. An inverter is controlled by using particle zone optimization using space vector modulation. Here we have a different tip speed, say between beta equal to 20 to beta equal to 0 degree. We can have a look how the coefficient of the turbine speed varies, the maximum value of 16.2 x. So 0.5 you can able to get if it's going to be 0. If it is going to be 20 degree, we'll be lying around the 1.15 of your coefficient performance of the turbine. So this is very important to control your synchronous machine and to get the maximum power delivered to the induction drive system. So in order to do these algorithms, what we have done with the artificial B colony algorithm, what we proposed as a MPPT model, maximum power point tracking, we took around 50 numbers of iteration parameters, and total run time is only 15. And desired error is going to be 10 power minus 6. For this, we took a total foot source, which is around 20, and number of B for searching is going to be 10, and onlooker B is 10. So it's a very small compact system based on various experience we gained from the test module. We restricted the module to very small values. We start the program, we feed all these parameters to the system, and the system start finding the finest values of the fitness function. Once the fitness function is available, it runs the motor to find the values of the various speeds, torques, etc. And we are trying to look at all these parameters through hydration, because the hydration is around 50. So it top ups, it goes for until 50 hydrations, the loop will run away. Then we find an optimal value, then we start regulating the systems. So how we regulate the systems, we look all the parameters, speed, torque, voltage profile, current profile, all is okay, then the system will run. But for this, we took only minimum time because we took only 50 iterations. And this is the simplest module I like to show because to avoid complex algorithms, we have a particle swarm optimization algorithm which used to control the PI regulator to generate always like new values of KP and KI, and we don't use any feedback anti-wind up action within the PI regulator because that will be done by PSO. So speed is compared with the actual speed of the induction drive, and the error is given to the new PI regulators. From that, we calculate what is a synchronous speed. From the synchronous speed, we are adding with the rotor speed to get the new value of slip, and the slip is multiplied with the gain to a lookup table. We have V by F controller here, which is a lookup table, which has a x-axis of frequency and y-axis as a voltage. For example, if the frequency is 0, output voltage is 0. If it is going to be 50, say rated voltage of the system. So then that has been given to a ABC control to convert all the three phases into stationary reference frame for controlling active power and reactive power, or I can say torque and flux. We are giving to the space vector modulation that will regulate the inverters to required speed. So all these conditions, you are able to regulate the induction drive to appropriate level from the different powers. What we are doing with the PSO algorithms on the inverter module, we start the program. We are positioning the swarm particles. Then we calculate the fitness function. We update the value of KP and KI, and we run the system. Look at the speed, torque, as I said. Evaluate all the performance. If all the performance is okay, we stop the regulation. If not, we will update the fitness function and we find the new values. So in this case, it's very important. The slip speed is added to the rotor speed, as showed you in the closed loop control algorithms. And here the convergency rate is very faster because we are comparing between ABC. We have two different hybrid control algorithms. One is by ABC, one is by PSO, which have multiple AI algorithms within the systems. So the trade-off is more accurate and we are very precise for the stable response. All these programs are parallelly running in MATLAB along with the DSpace processor for efficient control. And these are the performance. You can have a look. We are trying to look at what are the power generated from, particularly from the photovoltaic panel. It's not pure DC. You can see huge oscillation at the high power generations from the maximum power generation from the photovoltaics. And of course, this is the power, and this is the power, and this is the current. Has a huge oscillation, and we are trying to keep to match always the maximum power point even under various irradiation conditions. If you look at a close view, you can see how much deviations, oscillations, or I say DC ripples of AC components available in your photovoltaic panels, power generations. But when by using these hybrid control algorithms, what we propose, we are trying to regulate the power constant from the photovoltaic panel. You can have a look voltage, and we try to regulate the current and power at a different scale, but we are always trying to keep at the maximum power point, which is visualized at the output side of the induction drive. The currents are very smooth, even though there are huge oscillations and perturbations created within the insulation and isolation of photovoltaic panels due to the partial shading effects also. But all the cases, the currents are very smooth, sinusoidal in nature. The speed is very smooth. We are regulating at different levels. We are trying to create a different insulation from the photovoltaic panels, of course, partial shadings. All the speed is very smooth. Torque is very smooth, and of course the DC bus voltage is very important. It is very stable, driven for the drives, and this can be easily noticed with these results. We are trying to regulate the photovoltaic power from 1000 back to 500, back to 800, 300, and back to 600. All these regulation conditions, the induction drive voltage and current are very smooth. They are unity power factor, sinusoidal in nature, so that we get a very good power quality of the induction drive. And this shows you the flow rate and the head of the wind turbine. You can have a look from 0 to we went to the maximum, and the head is also maximum. I mean, from the induction drive pumping rate, I'm talking about the induction pump rate maximum, and the head also maximum. So but the parallelly we are having a lot of insulations from the photovoltaic panels. But all these conditions, the waveform of the current generated from the induction drive is very smooth, sinusoidal, and we have a stable DC link voltages, and it is not been started. That's very important for a high quality waveform and precise control of the induction drives. And this gives you a clear idea. We have developed many artificial intelligence hybrid algorithms based on PSO, ACO, and ABC. All the cases, ABC provides a minimum number of iterations and within the required runtime. So our runtime is like 15, and we are finding all the times the iteration is less than 10 for ABC algorithm. When you are comparing between ABC and PSO, you can have a look the error produced, how accurate. So the error is very minimum in case of ABC, which is around 10 power minus 9, whereas for PSO, which goes around 10 power minus 6. So this gives you a clear idea how the convergence rate has been done for different algorithms we tested in real time, but I didn't present everything. But ABC always converges at a very high speed when compared to fuzzy logic or ACO or PSO algorithms. This gives you a clear idea how the first quadrant operation of the drive systems produced with the new proposed ABC algorithm is much faster and convincing the requirements. And this will give you a much clearer idea. We have shown you with the partial shading conditions. You can create. We have created three different patterns of creating a different partial shading effects: 25%, 30%, 35%. All the cases, if you look at the transitions or transient behavior, in case of PSO is very high, a lot of oscillations. You can visualize from here. When compared to PSO, ACO algorithm has maintained much stable values, but always, as I said, ABC proposed algorithm, it maintains the regulation in a very short time with a minimum oscillations and faster stability. You can have a look much improved. So all the cases, you can have a look the proposed ABC algorithm what we developed as much good efficiency in controlling. I mean, this is not the overall efficiency, the efficiency of the algorithm to track and respond faster, which is around 99.9% all the cases in three different patterns. Finally, I like to show you some quality waveforms how we generated from the these analysis of different hybrid modules. We are always trying to keep a total harmonic distortion which is around 2.6% and 2.8% from different levels of the voltages which are generated by using these electronics converters. You can have a look how the regulation has been done for in real time for the photovoltaic power, current, and the voltages. But still, all these perturbation, high profile voltage is maintained from your induction drive as well as the current, which are unity in nature, and stable power from the photovoltaic has been regulated as an input to the inverters. And this is very important. We are always try to have a reduced voltages in the total harmonic distortion in the voltage and the current, which is around 2.6% and 2.8%, well below 5% IEEE standards. Due to the time restrictions, I'm little moving faster. For example, this gives you a clear idea how the conventional perturb and absorb algorithms generates photo oscillations. But with our proposed algorithms, we have hybrid modules. We use ANFIS, which is having a fuzzy logic and a combination of PSOs. We try to develop our own new algorithms as a hybrid module. Then you can have a look how the powers are well ensured for reducing these all harmonics and oscillations. And most important, all the cases we are getting the tracking seconds, or how much seconds all these perturbations are reduced is less than always 1 second for the combination of hybrid and FIS PSO algorithms. So this is very important why we are using hybrid control algorithms to monitor different parameters within the large renewable energy integration with the grid as well as with the electronics converters. Here I can show you how it has been calculated, the precise value we calculated. For example, when we are using PSO or ABC, we also used IoT sensors because IoT sensors doesn't have a cable and it can be placed at a location within the setups, and all these informations are collected through internet and we are processing with the fast computers so that the computational behavior is low, simulation period is less, and of course accuracy is very high, and energy losses are reduced, and tracking velocity is very high. Hardware complexity is moderate, yes, because we have sampling errors because it has to collect the details through Wi-Fi. Then we have to process in the computer. There are some sampling losses, but we have algorithms to monitor that and enhance the capacities. So of course the cost is appropriate. Then how we are calculating all these efficiency For the calculating the efficiency, we are calculating what is the maximum power extracted from MPPT during the time T max, and we are dividing by available maximum power from the T max. So then we get different efficiencies of the algorithms, not the overall system. It's very complex. So PSO we are getting 95.13 percentage, ABC we got 97.68 percentage, and PSO when it is integrated with IoT we get 99.9 percentage efficiency of the algorithms for tracking. And this will give you a clear idea how the efficiency has been tracked by using hybrid control algorithms. And finally, I like to conclude my presentation that in the future we are going to have from a hybrid model of electric vehicles, which is going to have batteries, supercapacitors or ultra capacitors, along with the fuel cell as a main train. So the future focus are towards developing new low-cost fuel cell electronics-based powertrains, which has become a prerequisite through using microgrids and smart grids. Battery technology has to be replaced with lithium-ion because they are limited in lifespan. Of hybrid model of storage technology. Of course, these batteries in the future will be integrating to the grid. So we have to look at different dimensions on voltage instability, harmonics, voltage sags. So we have to develop a smart grid technology which can able to mitigate all these problems in an environment where AI will play a critical role. Of course, as I said, 250 million vehicles will be roaming around, and we have to think about vehicle to grid communication and grid to vehicle communication and home to grid and grid to home communication by using smart metering. I give an example on IoT sensors, and integration of all these renewable energy systems needs high stability penetrations. In the future, we are going to have many hybrid AI algorithms in practice for precise and accurate tracking, because it not only used within the electric vehicles or microgrid system, it has to enhance along with all the renewable energies are integrated by using blockchain technologies or machine learning algorithms and cloud computing, etc. As an example, I showed you with an hybrid model where we used IoT sensors for fast tracking efficiency and a different environmental condition. Of course, I didn't show you about self recovery and resilience because of the time restrictions, but these all can be done but with all these hybrid module of electronics integrated controllers. And thank you very much for your attention, and if you have any questions, I'm happy to respond. If you have any questions, I'm happy to respond. And thank you very much for your invitations, and I look forward to seeing you. Thank you very much. You are all welcome to University of Southeastern Norway to do your internships and etc. I welcome you all. Thank you very much. See you all. Bye.
Hi, I'm available. Yeah. Good evening. Yeah, we can start. I'm not allowed to, turn on my camera using the link. I'm not sure. The link is not allowing me to open the camera. But still, okay, my camera is not able to detect. I'm not sure using the. Okay, I will rejoin again. Uh, Still, it is not allowing me to share. Which it's okay. It's okay to share the screen. Okay, I'm not sure what is the issue that camera is not allowing. Okay, you can see my screen, right? Yeah, yeah. You want me to introduce myself, or you'll be giving a? Okay, okay, okay. Thanks. Thank you very much for the nice introductions. And good evening, all of you, once again. And thanks for inviting me to the as a keynote speaker for the conference. The topic is about blockchain technologies for microgrid system. And myself, Dr. Veera, you can call me simply Veera. And full name is Veera Pandian Veerasamy. I'm working currently as a research fellow in Energy Research Institute or a clean energy research lab at NTU, Singapore. Basically, Energy Research Institute, research institutions which handles only researches related to energies, and it is a subsidiary of NTU itself. And as well as, in spite of my research fellow position, I have been a part-time lecturer teaching the master courses in School of EEE NTU. And the point of contact for me is through email IDs. You can use the professional ID from NTU as well as my personal Gmail if you have any of the queries for or any collaborations in future. So before I go into the today's topic, I'll just explore a few things, my research areas and myself. And myself, Veera, I've been doing research and most of the time in AI applications for power system optimization and control. Most of the topics that I cover in my research areas are peer-to-peer energy trading, load frequency control, voltage stability and control, power flow, optimum power flow techniques, power quality classifications using deep learning classifiers, and high impedance fault detections. So high impedance fault detection is a special scheme of a production schemes where the path of the impedance path will, the faulty path will have the high impedances rather than the conventional fault. In case of a conventional fault, the impedance will be zero. Whereas these high impedance fault are also called as, when you have a fault on the insulators, the fault is happening on the insulators, or a highly impedance is, it holds a memory which has a memory to store the past values of the system, so that it is helping to reach the optimization in a faster way, so that the system can behave in a more efficient way. So this recurrent Hopfield neural network can be applicable to any of the power system applications. Since our power system applications are most of the time is a dynamics related to dynamics, so most of the power system dynamics problem can be well designed using the recurrent neural network compared to the feed forward neural network. So in addition to that, I've been exploring a federated learning approach. Is an advanced learning approach. The federated learning we also called a distributed learning. So distributed, instead of learning a centralized way of neural networks, nowadays we are learning using a distributed fashion of neurons. So through that, we are trying to optimize the performance of a neurons, and then the results of accuracy will be improved for the neural networks, whichever the networks we are trying to use it for the applications. In spite of this, I've been working on a meta-heuristic algorithm. Specifically, I've been working on a PSO techniques, and I think the previous keynote speaker, Professor Sanjeev Kumar, has been explaining most on the meta-heuristic algorithm. I also as a part of the listener. And then I've been working on a clustering and deep learning classifiers. If you ask me the clustering, where it will be useful is when you're having a group of power systems, that is a group of systems in power systems, where this group of systems you can group it based on either a low voltage or a high voltage. Based on the system voltage levels, we can classify it. That can be done using a clustering applications. So in spite of these AI techniques, I have been working on differential privacy schemes in terms of a cyber security attacks in the microgrid and distributed control of a microgrids. And apart from these simulations and softwares, I have experiences in polarity hardware in the loop simulations, and as well as operation of 0.125 megawatt microgrid in clean energy research lab, as well as 1 megawatt microgrid in EPGC. EPGC is again a subsidy of under ERIAN, we call Energy Research Institute. Right? So EPGC stands for Electrification Power Grid Center, where we have a location of a 1 megawatt microgrid. The microgrid has been connected to the Singapore power grid. So in Singapore, the largest microgrid is 1 megawatt microgrid, which is located in EPGC. So which is located in a Jurong Island, which is an island. It's not in the city, it is a remote places. In order to maintain the safety, the microgrid has been operated in an island. So what we specifically do there is testing of EV chargers, where we test the EV charger based on the standards, IEC standards, as well as a Singapore standard called TR25. So we test AC chargers as well as the DC chargers, and we do certification because our lab is an accredited lab. It's a Singapore aggregated by Singapore Accreditation Council. So we have been testing and approving the TR25 jobs. In addition to that, I've been involved in testing of a power management solutions. Nowadays in Singapore, we have a HDB blocks. The HDB blocks, they call it as a house and development board, where they do is they allow the Land Transport Authority, which is an agency for maintaining the transports, to install EV chargers in almost all over the Singapore. The plan of a Singapore government is to install at least 60,000 EV chargers, AC chargers by 2025, so that it can facilitate or increase the EVs vehicles in Singapore. Because the energy transition in Singapore to meet the net zero carbon emission is by 2050, means that by 2050 Singapore will become a carbon emission free country. So that in order to promote that, Singapore government is trying to make a decision that to install the EV chargers in HDB blocks for the common users. So the EV chargers cannot be installed just like that. The EV chargers itself need to go through the certification job, means that it should be tested and certified well, and then The EV chargers is controlled by a solution called power management solution. It's nothing but a controller. The controller, what it does is it will use the excess power whichever left over by the HDB blocks, which is a housing or the apartments. Whatever the excess power which is left over after using the HDB blocks will be used by the EV vehicle. Say for an example, if I have a 100 ampere current, so my building load is only 40 ampere or 40 ampere or 60 ampere. Then yeah. 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 I'm still here in explaining the power management solution. What is the necessity of this? No. I didn't step into the topic. Yeah. So this is why we tested the power management solutions in Singapore. So and then we are testing the ESS for the grid services. The grid services basically we tested for frequency regulation services, contingency resource services, and demand response services. So what is the type of ESS we are testing is we are trying to test first life and the second life batteries. So in our lab we are trying to test the first life, and the second life we call it as a EV vehicle batteries, which are used for more than a years and will be disposed. Instead of disposing, we'll be trying to use those batteries, collect those batteries, and try to use it for the grid services. Apart from this, I'm using I'll be expertise in some of the software packages like MATLAB, Python, PLC programming, and LabVIEW. And here I would like to say sorry for some things, because the testing of EV chargers, power management solution, and ESS for grid ancillary services is a current ongoing project. I cannot share the slides because it's like is within the rule that when the project is ongoing, we cannot share the ideas outside, or any kind of images we cannot share it. That's why I could not share the images here. And yeah, forgive me for that. And yes, yeah, we'll go to the today's topic, blockchain for microgrids. Yeah. So blockchain, basically we'll be introducing the blockchain for the case of security. And here in the microgrid, we are using for energy trading applications. The blockchain here we are using for energy trading applications. And when the energy trading is happening, how we are going to control the microgrid, that we are going to see today. And what type of a controller, how we are going to design the controller is a simple PID controller. The controller will be tuned based on a federated learning approaches, and we'll be implementing the controller both in a polarity hardware in the loop, as well as in a real-time microgrid. So we'll be going through the topics of blockchain and the microgrid. So this outline of our overview of today's speak on the topic. First, we are going to see is a blockchain-based peer-to-peer energy trading in microgrid initially. So if you ask what is a blockchain, is actually the blockchain is a chain of blocks. If we see here, we have a chain of blocks which is connected. So each block will have the timestamp of its move, and will have a contract information where what are the information need to be protected, and the transaction histories of the peers who is going to sell the power to the neighbors, and which is protected using the hash code, is something like a cryptography that we are using in a computer science. So the concept is similar to the Bitcoin. So the blockchains is used to include all the content, whatever the transaction contents which is happening between the two parties will be included in the smart contract, and this contract will be executed in each blocks, and each block's consensus is maintained using a consensus protocol. So using a consensus mechanism, each blocks can communicate each other, and it will be at each node will be timestamp, as well as each transaction inside the blocks will be timestamp. This is what the blockchain was. So if you ask the question, if the blockchain can be applicable only for energy trading application or some other application, can. The blockchain can be used for either designing a controller, or if you want to protect any kind of information, if you want to protect control information, or if you want to protect the controller, what you need to do is you just need to write a set of codes, and these codes need to be implemented in a JavaScript where the smart contract will be developed, and this smart contract will be included inside the blocks. So if you can see here, there is a series of blocks which is connected in a form of a chain, and each blocks is having the specific unique hash codes, and which is trying to maintain the security of this system, whatever the information which it has. So basically, we are using for a peer-to-peer energy trading application. If we ask what is a peer-to-peer energy trading application is, in a conventional grid systems, we are being trying to get the power from the utility. So most of the time, the utility is selling the power to the residential people or the utilities. So we call the residents people with the called as a consumer in the case of a conventional grid. Whereas in case of a modern grid system where we have a peer-to-peer energy trading, the residential users will be generating some means of a power, either using a solar PV or a wind farm or a energy storage devices, or it can be even an EV vehicle. And these residentials is willing to sell the power either to the grid, or they are transferring power to the neighbors or neighbor residents. Then we call as a peer-to-peer energy trading. It's like a peer-to-peer communication. In a communication theory, we have a peer-to-peer energy trading systems in a electrical systems. So in a peer-to-peer energy trading, we are supposed to have two important factors. So one of the factors is the consumer, who will not generate any kind of a power, but who will consume a power from either the peers or the grid. Whereas in the case of a prosumers, who will generate the power as well as who will consume the power. So the excess amount of a power, whatever he or she consumes, will be sent to the neighbors, or it can also be sent to the grid. So in this case, we are applying the peer-to-peer energy trading techniques for the microgrid system, and therefore it is no more grid connected system. And if you ask the question, it can be applicable to a grid. Yes, it is applicable to the grid connected system. But in our case of laboratory testing, we check with the microgrid system. So the prosumer is nothing but who generate as well as the consume power. The consumer is only consuming the power. So generally, the energy trading happens how is based on the cost. So generally, a prosumer will be bidding some amount of a cost, how much that he is willing to sell the power, and the consumer will also bid the cost, how much he is willing to buy the power. Say some X is based on the how much the lowest price the prosumer can bid. So how much the consumer who's paying the highest price, based on that the market will be clearing. So what is the advantage of having this peer-to-peer energy trading is, the advantage is it is an open market, anyone can participate, and the cost of the utilities bill will be reduced compared to the conventional grid system, because it is a more competitive network, and it is more reliable compared to the case of a grid system. Because in case of a grid system, there is a chance the grid may be lead to a failure, and it leads to a sometime blackout. And what happens during the blackout is will run out of a power. There will not be any power supplies to the system. Where in the case of a peer-to-peer energy trading, what happens is, since it is between the neighbors, even a blackout happens in a microgrid system or a grid system, it will allow you to send the power partially by islanding the faulty part of the system. So by this, we can improve the reliability of the system. We can improve the reliability of the system, as well as we can also reduce the cost of the utility bill for the consumers. So this is a more advantage of a peer-to-peer energy trading, and how the peer-to-peer energy trading operators based on the double action mechanism. So the double action mechanism theory says that by arranging the generators in the from the lower order to the higher order, so you arrange the generator with the price in the increasing fashion, and arrange the consumer whose price in the case of a decreasing fashion. Say for an example, A1 is the cost of generator 1, and A2 is a cost of generator 2, and A3 is a cost of generator 3, and A4 is a cost of generator 4. In this case, B1, B2, B3 represents, B1 is a consumer cost 1, and B2 is a cost of consumer 2, and similarly like that. So in this case, what happens is, the generator who is having the lowest cost and the consumer who is having the highest cost will be given the priority to participate in the market initially. And the market will be clearing at this point, and we call this as a critical clearing point, or equilibrium point, or a clearing prices. And in case of clearing prices, we still have two schemes. One we call as a uniform pricing, the other we call as a non-uniform pricing. In case of uniform pricing, in spite of whatever the bids of a consumer or the prosumers, at what value the market is clear, the the money will be paid to the prosumers and consumer based on the market clearing price. If we follow the single price for each of the prosumers to pay, then we call as a uniform pricing. Suppose if you're using the concept of what each individual producers has been bidding to pay, then we call as a non-uniform pricing. Means that in case of non-uniform pricing, whatever the amount the generator people whoever ask will be paid the value, and there will not be any common value. They will not be paid with the clearing price value. I can say for an instance, the market is clear for 10 rupees, and the generator one is, say for an example, is selling the power 1 kilowatt for 1 rupees, and generator 2 is selling the power for 1 kilowatt for 2 rupees, and 3 for the case of 3 rupees, and 4 for the case of 4 rupees. And in this case, we assume that consumer 1 is buying the power for 10 rupees, and consumer 2 is buying the power for 5 rupees, and consumer 3 is buying the power for 3 rupees. We assume in this case. So you can see here the market will be clearing at 3 rupees. If I pay 3 rupees for all the producers, in spite of whatever the quote by the consumers, then we call this a uniform pricing. Suppose if I pay whatever the amount asked by the prosumers 1, it is 1 rupees for 1 kilowatt, 2 rupees for the generator 2 prosumer 2, and 3 rupees for prosumer 3, then it is called a non-uniform pricing. So if you ask another thing, what will happen? The people who is not clearing the market is they need to participate market the next interval. So how long the intervals take is every 15 minutes the intervals takes. So they need to wait for every 15 minutes, then they need to clear the market for the next slot, so that if they clear the market, they can participate in the trading. If not, they cannot participate in the trading. So the blockchain mechanism that we use here is a private blockchain, and the mechanism we use is a proof of authority of consensus mechanism. So you can also use a public blockchain. Is based on whether you want to use a private or the public is based on your applications that you use. So how we can implement this blockchain for the microgrid network or any kind of physical power system is, we know that we have a physical system. And this physical system has been controlled by means of some kind of a local controller, and we have a physical layer at the bottom, and we have a control layer. This control layer will be communicating to each physical device via the TCP/IP communications. So what happens is, the information for this control layer will be coming from the energy management system in the actual power system. Will be coming from energy management system. The energy management system will be running your 24-hour dispatch as well as a 30 minutes dispatch command to the controller. Where in this case, the controller is getting the information from the peer-to-peer. So once the market peer-to-peer energy trading is clear, that whatever the market is value is clear, the generator need to dispatch, then this command will be given to the controller. Then the controller pass the command to the generator, and then it is trying to dispatch the generator whatever the value is asked. Since this, if you ask me, there is a energy management system for this case. Yes, of course, we have an energy management system. On top of the energy management system, the peer-to-peer energy trading is also working based on the blockchain. So the blockchain layer will be the top, and then followed by the middle layer of a control layer, and then we have a microgrid hardware layer. So what we are trying to secure here is the transaction information between the two peers, whatever is happening, will be more secure, because we are promoting some kind of an open market. So there is a chance that any one of them can go and change the transaction history so that the fraudulent will occur. So in order to avoid those things, if we introduce a concept called a blockchain, and if you secure the transaction inside the blockchain, so there is a trustworthy between the people who's willing to sell the power as well as who's willing to buy the power. So in order to increase the security as well as increase the trustworthiness among the people who are sharing the power, we use the concept of a blockchain, as well as these blocks will be verified at any point of contact. So if you feel that there is some fraudulent occurs or some kind of theft occurs in the case of billing process, so you can go and recheck the blocks using the hash codes, and the possibility of hacking this is very, very difficult. It's not so easy. So how this blockchain works is based on 3 different phases. So initially, bid phase. So what will happen initially, the bid phase is each prosumer or consumer who wanted to buy or sell the power, they need to bid the values as well as the amount of power they need to buy or the sell. This phase we call as a bid phase. In case of a reveal phase, they will verify and they will unmask the data, and they will be verifying whether there is a bid and offers are submitted by any of the prosumers and the consumer who wanted to participate in the market. The third phase we call as a clearing phase. The market will be cleared based on the bids value they are quoted, and either the market will be running through a uniform pricing or a non-uniform pricing. In our case, we assume that the market is running through a uniform pricing, and whatever the cost of the market is clear during the time, and this amount will be paid for all the case of generators. So we initially run through many simulations, and then we tested directly to the microgrid system. So this figure shows you the single line diagram of microgrid located in a clean energy research lab at the NTU School of EEE. So what happens here is we have some of the sources that is participating as a prosumer, and we have some of the loads, we call those loads as a consumers. So the entire microgrid is a 15 bus system, and we have a bus 1 will be acting as a programmable source. Bus 1 will be acting as a programmable source, as well as node 15 also will be a programmable source. And here in this case, we are not using a node 1, we are just using a node 15 only. So it is a programmable source connected. And then we have a synchronous generator, which is at node 2. And we have a programmable load. The programmable load is a resistive load bank, so which can be programmed using the Python programming. So you can command the load, how much amount of a kilowatt or how much amount of a watts that you need it for next. And then the industrial load is acting as a base load here. And this industrial load will not be controlled. It's a base load of 6 kilowatt capacity. And we have some resistive load at the node 6. And we have a capacitor bank for the case of a power factor correction and the case of voltage improvement. And in our case of a Singapore power grid system, most of the time the power factor and the frequency and the voltage of the system is very stiff, because the system itself is a very small grid system. So on node 8, we have another programmer source, but we are not using those sources. At node 9, we have a wind emulators or the simulators. So the wind emulator we use is a DFIG generator. And 10 and 11, nothing is connected. And in case of a 12, we have a supercapacitor, which is a connector. And 13, we have a 13 we doesn't have any connection, and 14 we have a solar PV emulators or the simulators, which is connected through a Harvey inverter of 5 kilowatt capacity, where we have a intermittency mitigations also in the same microgrid system later case. So all these equipments are at TCP/IP communications, and all the smart meters are are reserved with the static IP addresses. So all the communication is established within the microgrid system on the database, where the database server will be communicating to each devices using the TCP/IP protocols. So how we implemented it? In this case, we assume the prosumer synchronous generator is going to be the prosumer 1, and the battery which we are connecting is going to be the prosumer 2, and the programmable load is going to be the consumer 1, because the rest of the components whichever we have will not be controlled. So the only component that we can have a control is the energy storage devices, synchronous generator, as well as the programmable load. So remaining will act with your base generation and the base load. So we will demonstrate the peer-to-peer energy trading with our lab setup. So initial phase, as I told you before, the initial phase is a bid phase, followed by the reveal phase, and then followed by the clearing phase. So in the case of a bid phase, each prosumer and the consumers will be submitting their bids. So it shows you that the account address is in a hash code, and followed by the price of energy, which is means who want to submit, they'll be submitting it, and the execution will be happening. So they ask for the power of 2043, and these power values is given in terms of a watts, is not in a kilowatt. So in the case of reveal phase, whatever the amount and they ask for and whatever the power they ask for, it is shown here in the price and the quantity. And in case of a clearing phase, you can see that the market is cleared here, where the buying bids are here and the selling bids are here, and the market clearing prices. You can see this is a buying prices, and the red line is the selling prices, and this is a market clearing price. So the market clearing at one particular value, and we call as a uniform pricing in our case. And this is a transaction history which is happening between each prosumer and a consumer when we run the system. So how we run is we run using the Raspberry Pis. We establish a peer-to-peer connection using the Raspberry Pis and the server PC. So the Raspberry Pi will help us to communicate to each devices via the TCP/IP, because the Raspberry Pi also has its own IP addresses. So inside the Clean Energy Research Lab, we have a dedicated communication link between each devices, and this link can be pinged via any devices using the comms network. So the communication network you can ping from any part of an NTU. Yeah, it has been dedicatedly made like that, and you can see here this is a transaction history which is showing you that how much amount of power it has been sold out by the prosumer 1, which is a synchronous generator, and what prices. And this shows that the hash code, and you can see that the hash code for each account is different, but it will be unique for that particular account for the number of transactions you make. For this case, they have 3 transactions and you can see here, and for all these three transactions, it has a same ID. Means that this ID is reserved for the case of prosumer 1, and for the case of a consumer 1, the ID is different, and the case of prosumer 2, the ID is different. So the prices, whatever it is cleared, the market, and the amount of a power, whatever it is sold out. So you can see here, sometimes the battery can also be, you can see the actions for the case of bought and sold for the battery. Means that it is proven here the battery can be of it can be a load or it can be a generator, because it can charge and discharge, so that it can act as a both bought and the sold mode based on the need. And you can see here in the first case, the synchronous generator is selling 1 kilowatt of a power, which is consumed by programmable load of 600 watts, and the energy storage is consuming a 600 watts, and the market clearing price during this case is a 45 Sing dollar. It's just a 45. We assume it is a value, numerical value. So if you ask me, the prices will not be the same for the Singapore, but since there is a one limitation in Java, the Solidity language scripts. In case of when you code the things in a Solidity, the value it takes will not be a decimal; it is a whole number, whole numerical number. So if it can be 0.45, that is 45 cents in a Singapore dollar, 45 cents per kilowatt. So it has been referred here, the 45 cents. So the next transaction happened for a 40 cents. And you can see here the 400 is coming from the synchronous generator and 600 is coming from the battery. In this case, the battery is trying to sell more power compared to the synchronous generator. The reason behind is the synchronous generator in our case is basically emulating the diesel generator as a backup, as well as the inertia support for the microgrid. Whereas in case of a battery systems, the battery system is trying to store the energy, and it is a form of we are trying to emulate a EV vehicle or the power stored from the PV generations. So therefore the priority is given for the battery rather than the synchronous generator itself. So that's why the priority of dispatching of a power will be done first by the battery, followed by the synchronous generator. So in the case of a third transaction, what happens is, so the programmable load is again asking for 1 kilowatt of a power. Then 600 watts is spent by it has been discharged by the battery, and 400 watts is given by the synchronous generator. And these transactions is happening inside the blockchains. And since the transaction is happening inside the blockchains through the hash codes, and therefore the transaction is more secure, but we can still can visibly see what's going on inside the blockchains, at what time the transaction is happening, and when the transactions happen, and all those informations. So later part of things, the blockchains we also implemented in the mobile applications. So we have implemented the blockchain for peer-to-peer energy trading using a mobile application for a specifically Android-based mobile application. We didn't go to the enhanced level of iPhone level, because most of the time Android mobiles has been used in a common side. So we are trying to use Flutter-based programming to develop an applications, and we have developed a mobile application for the case of peer-to-peer energy trading. So in this mobile application will allow you to register using an email address to create an account, and then a verification acknowledgement email will be sent to your email to verify that your email and to create an account. And then you can key in the value in the market. The market page will be opening where you can key in the values, whether you are a prosumer or a consumer, and what amount of a power that you wanted to sell or buy, at what price you wanted to buy or sell. So then using the mobile application, you can execute the transaction successfully, and we executed for the same cases, and this is a transaction history for the system. So this mobile application is legally applicable only for a Singapore, and we have provided the YouTube link for the case of the mobile application, how it works. Maybe in a later part of my speech, if there is some time, I can show. If not, I can share the PowerPoint slides later. You can have a time. You can have a look how it has been working the system. So far we have been applying the blockchain for the peer-to-peer energy trading. So what happens if this peer-to-peer energy trading happens in a microgrid? So if it happens, if you have a frequent transaction in the microgrid, there may be a fluctuations in the system. So the fluctuations may lead to the frequency oscillations, or it can maybe lead to the voltage oscillation. And most of the time, the voltage of the system can be maintained by means of a capacitor banks or some kind of synchronous devices, whereas the frequency of the system need to be maintained by means of load frequency controls. So in the next part of my speech, I'll be concentrating more on the frequency control applications for peer-to-peer energy trading system in a microgrid. So in a general, we have a microgrid, we have several control schemes. Conventionally, we have a centralized control schemes. So any devices or any distributed generator in a microgrid will be having its own local control. We call it as a primary controller. So this primary controller, in addition to this, we have a secondary controller, and this secondary controller will help to maintain the voltage and the frequency of the system. So this secondary control can be of centralized fashion. If you have a secondary controller in a centralized fashion, where we have a communication link which is to the primary controller in this fashion. Where if we have a centralized, that is a secondary control in a distributed manner, then each distributed generation will have its own primary and the secondary controller, provided there is a communication link between each DG's secondary controller. And the third case, we have a decentralized frequency control, where we doesn't have any kind of external communication link. So if you ask me what is the difference of among these three and where we need to apply is, in case of a tight control of a system, if we need to maintain the consensus of the system, in that case, we need to opt for a distributed control. The centralized control may be leading to some kind of a failure. Suppose my centralized controllers fail, in that case, the entire system may not be operated. Whereas in this case of a distributed control, if one of the controller fails, still the system is more reliable to supply. So the distributed control will give you a more reliability, but it is prone to some kind of a cyber attack due to the large number of communication lines between the controllers. So in order to avoid these cyber attacks or a cyber security, maintain the cyber security, so we go for a decentralized system where we don't have any kind of a communication links, but we have a control of the DGs by its own. So in this case, each DGs will have an independent control, provided they track of frequency of the same system at the common bus. So we try to apply this, and we know that when you are having the frequency in the case of a highly dominated renewable energy systems, the frequency fluctuation will be higher. Therefore, the frequency in order, if you see here, it will be having a very lower value. The frequency dip is higher because of the lower inertia compared to the conventional system. Whereas a conventional system have the higher inertia, therefore the frequency dip will be somewhat higher, somewhat low, is improved here. Where in this case of a low inertia system, where we have more amount of renewable energy, we have a highest dip. So in order to in order to control this particular dip, we will be having the secondary controller. So this kind of a secondary controller need to be designed more robust in power system. In order to design a more robust, we need to go for some kind of a dynamic controller to handle this dynamics. And this dynamic controller will be, in this case, will be designed by the dynamic neural network. We call this a recurrent neural network, because only the dynamic neural network can store the memory of the system, so it can react and it can be sometimes proactive for the system to maintain the stability of the system. So again, it's the same cases where we have the microgrid setup here, and we have a controller, and we have a blockchain layer, and we assume that the blockchain is happening here, and the secondary controller will be implemented in the control layer, so that it can be control whatever the devices which is participating in the frequency regulation services. So in a conventional case, any kind of a microgrid system can be controlled directly via the primary and the secondary controller by tracking the frequency of the system. But in case of a peer-to-peer energy trading system, it is not the case, because the peer-to-peer energy trading system itself is an open market system where it follows the structure of a deregulated system, provided we have a concept called a small contract participation matrix. So this kind of a small contract participation matrix will help you to participate in the frequency services, where each prosumer who are willing to participate in the frequency services, those information will be collected and included in as a smart contract inside the blockchain, and this blockchain will be implemented inside the Raspberry Pis. So we have done the same. The difference between the conventional and the peer-to-peer energy trading system is we have an extra additional information which is coming from the smart contract participation matrix. It is similar to the deregulated system where we have the contract participation matrix for the frequency regulation services. So there is some changes and the rules, but the concept is more or less similar to the deregulated system applicable for a frequency regulation. So what the smart contract participation matrix says is, who are the prosumer want to participate in the ancillary services in addition to the energy trading. So their services need to be arranged in this, and they need to clear this matrix. So it says that the rows will be representing the prosumers generations G1 to Gn, and the column is representing the demand value of the consumers D1 to Dn. So at any time, the sum of the column need to be 1. Means that the column 1 is 1, means that the load at the D1 will be satisfied fully. At any time, if you satisfy the load at the point at D1, then only you can move to D2. And similarly, if you clear the load at D2, then only you can move to Dn. But this is not the case in case of a deregulated system. So the rules and the regulation of these things has been written in a published paper, Smart Grid. I can share you those references later. So this is one of the concepts where peer-to-peer energy trading system is in top of the peer-to-peer energy trading system. The prosumers can also participate in the frequency services, and they strictly adhere to this kind of a contract participation matrix. So if you assume the G1 is supplying a power to D1, and if you assume that the G1 is supplying 1000 kilowatt and the load demand for a D1 is 400 kilowatt, in that case, G1 will supply 400 kilowatt to D1, and the remaining 600 kilowatt will be supplied to D1. So in this case, the G1, G2, and Gn and D1, D2, Dn prices are also follow the double action mechanism. They should follow the double action mechanism to participate in the ancillary services. So this kind of contract participation matrix controller for a frequency regulation applications. So in our scope of a study, we limit to the frequency regulation, and we assume that the voltage of the system is maintained constant, and we done the analysis for the system. So for the secondary controller, we use a recurrent neural network. As I told you before, the recurrent neural network itself is a dynamic neural network. The dynamics works based on the gradients of the neural network. So the type of neural network that we use is a Huffel neural network, which is proposed by the John Huffel in the year of 1982. And this shows you the structure of the Huffel neural network, which is a single layer network. So single layer network is, it doesn't have hidden layer. The speciality of this particular neural network is it doesn't have the hidden layer, and it has the input and the output is the same. It's a single layer. It doesn't have an input layer, hidden layer, and output layer like a conventional neural network, but it has a one layer where it can get the input, and the feedback will be feedback to the system. The output will be feedback to the input of the system. So we call this neural network as a single layer neural network, or it is a gradient neural network, or dynamic, or it can be a recurrent. So since John Huffel is a physics scientist and he developed based on the energy phenomena of the system, he says that if a neuron is doing some kind of a job, initially the energy will be high, and when you calculate the energy of the neurons, when it over the time, it will be keep on decreasing and reaching some stable or equilibrium point. It means that the equilibrium point, what he defines as, he says that it is reaching the stability of the system. Means if the neuron does its job and reaches a stability of the system, it trying to reach the solution of the system. So this explains you the mathematical explanations of how to apply the Huffel neural network for any kind of applications. So in order to apply the Huffel neural network, we need to define the energy functions. So the energy functions is a GI is representing a nonlinear function. It can be of any kind of optimization function that you need to minimize, and the weights of the function will be defined based on the gradient of these energy functions. So the gradients is nothing but the partial differential equations, and x1 to xn represent the number of neurons or the number of output variables that you need to determine. So in our case, we use a simple mathematical concepts where I can say that if the partial derivative of if the partial derivatives is going to be a 1, then I can say it's a fractional. It is following the partial, the integer order system. If I introduce a term called alpha to my gradients, and if I vary my gradients between 0 to 1, I can call this as a fractional order system. if my alpha is less than 1, I can call the same system as a fractional system. If my alpha is equal to 1, then it is called a conventional neural network. My alpha 1, we call it as a second order neural network. So we have studied for a different cases how the system works, and we identify that for a case of a fractional order system, the system performs very well compared to the conventional order neural network systems. So we also studied a higher order system. As of time concern, I cannot share the results related to the higher order system, but I can share some of the concepts related to the fractional order systems. So how you design a simple PID controller using the half-wheel neural network is, we define the energy functions of a half-wheel, and we assume that the energy function now here is based on the function to be minimized. For any controller, the error function is the function to be minimized, and the error control is the difference between the reference value and the planned actual value. So it is 1/2 is following the Lyapunov second order theorem. So when it follows the Lyapunov second order theorem, is trying to define that the energy function to be 1/2. It is the optimization or the error function to be minimized square. So we try to expand the Y plan as with the operator T, where T is a time operator here, and we expand the PID equation, the control law, and we try to derive the dou E by dou Kp in order to find the gradients, and we finally simplify to get the in a generalized form where of d alpha kp, d to the power alpha ki, and d power alpha kd. And here we can play around with the values of alpha. If the value of alpha is less than 1, the same neural network will be helping to obtain the fraction order neural network. If it is greater than 1, it will act as a second order neural network. If alpha is equal to 1, it will act as a integer order neural network or a conventional neural network. So if you update the dynamics of a PID controller using the KP-KI-KD rule of this one, then the controller can behave like an adaptive controller, self-adaptive controller, and which can handle the dynamics in a more appropriate manner compared to the conventional neural network. So in addition to the fraction order system, we also design called federated learning approaches, where the case of federated learning approaches is nothing but the distributed way of learning the neural networks. In my case, I apply to the neurons is a distributed way of learning the neurons. And you can see here in a previous case, the weight equations is the present state is equal to the past state of the weight minus multiplied by the gradient of the network. So here the same thing is replaced. The gradient of the network remains the same, but the past state of the network will be replaced by the aggregated weight. So the aggregated weight is designed based on the connection between the neighbors. We can correlate the information, that is the weight of the particular neuron can be based on not only the particular neuron, also based on the neighboring connection. To explain in a simple way, you can assume that I have a neuron K, where the neuron K is connected to the neuron I and the J. The weight of the neuron K, it not only depends on the weight of the K, also it depends on the weight of the neuron I and J because of its communications. So if it follow the communication, then we need to consider the weight of, if there is no communication, then the value of WT of Ti and WTJ becomes 0. Since there is a communication, and this is introduced by a factor for a generalization purpose alpha, and this alpha is a communication factors. If you have a communication between the neuron, the factor becomes 1. If there is a no communication, the factor becomes 0. And there is something like a step size to improve the convergence. We call this step size the consensus step size, because we need to maintain the consensus between each neurons, because all the neurons trying to operate in a distributed manner. So now if you update the weight of the neural network using this updated federated learning method, and we try to approach optimization, and the results become more efficient compared to the stochastic gradient method of optimizing the neural networks. We try to implement the concepts of peer-to-peer energy trading with a frequency control. I know is too many concepts. So how we implement too many concepts together is, so initially we run the peer-to-peer energy trading. So we have a setup within the microgrid setup in the polarity systems, where each DGs is controlled by the PID controller. The PID controller with the DGs is designed inside the polarity system, and this this microgrid model itself as a communication to the each Raspberry Pis and presenting the prosumer and the consumer. And the information coming from the Raspberry Pis are a peer-to-peer energy trading as well as a supplementary control information. The communication between the polarity and the Raspberry Pis here is form of a UDP, user datagram protocol. So we have a network switch, and this network switch is helping to connect to the each Raspberry Pis. In our case, we consider there is a 4 prosumers participating in the trading and 3 consumer participating in the trading. And the trading information and the energy trading information is written in a contract within a smart contract, and we implemented the smart contract inside the Raspberry Pis, and the blockchain has been implemented on top of it using the web3.py. So we run it and we send the reference signal to the each DGs from the Raspberry Pis, so that the Raspberry Pis will be communicating to the UDP to the polarity. The polarity system is having the microgrid system inside it, and you can see that. So the entire system will be in the microgrid, and this is implementation is done using the Raspberry Pis. So this is a physical setup for the system, and we have a polarity here, and we have a server PC over here, and you can see the set of Raspberry Pis which is acting as a prosumers, and set of Raspberry Pis which is acting as a consumer. And among this itself, we are implemented in one of the Raspberry Pis to support the supplementary controller to pass the information to the reference DGs. So this slide shows you how to implement it in our polarity. So in our polarity, we have a master and a slave, and within the master itself, we have a prosumers and we have a consumers. And the prosumers here, we are using a synchronous generator, wind model, solar PV, and the battery. So the consumers are the low demand, which is coming from the system directly. And we can see here the polarity facilitate you to connect to the Raspberry Pis using the UDP special communication systems, and you need to reserve the IP address for each of the Raspberry Pi devices. And we have implemented for the case of a 2 controller fraction order RNN control, and the fraction order RNN control with the federated learning. So the this is the slave of the system. And if you see here, the power dispatch from the each DGs from the microgrid when you use a different control schemes, and the frequency regulation is carried out for the case of each type of a controller. And this case for the polarity, in the case of simulation, we have validated with the 4 controller. When we are implementing in the polarity, we implemented only with the F4RN and F4RN and FL controller. So this is a peer-to-peer energy trading results when you have a 7 different types of peers. So 4 peers as a prosumer and 3 peers as a consumer. The line shows you the price, and the orange line shows you the power here, which is participating in the market and clearing the market. So the peer-to-peer energy trading is happening in this fashion. And then the dispatch command by each generators or each prosumers is given for the case of a frequency regulation. And you can see here the frequency of the system is tightly regulated by means of a FL-F4RNN compared to the F4RNN control. And again, we can claim that both the F4RNN and FL-F4RNN control is within the band. And we know that the frequency regulation standard says that the frequency should be maintained within plus or minus 0.2 hertz. So if by seeing the results, the frequency is maintained between 49.8 to 50.2 is within the limit of a standard frequency limit. And the right side shows you the power capacity that each prosumer is participating in the peer-to-peer energy trading. And the total of the microgrid generator is at 2000, which is 2 megawatt. So, and comparing the results, so we can say that the FL-FORL control is performing better compared to the other case. And this is a SCPM matrix for the case of a comparison we done in the simulation. And it is seen here that the settling time of the system has been reduced, and the peak overshoot and undershoot has been reduced compared to the other conventional controllers. And also we can see here the convergence for the case of RNN, F4RNN and FL-F4RNN. We can see that the energy profile. Hello? Yes, sir. Yeah, sure. Yeah. Just since we are running out of time, this from the FL-FRNM control is performing better compared to the other controller techniques, and we have implemented the FL-FRNM control in a microgrid in the Clean Energy Research Lab, and this is a single line diagram for the microgrid setup in the Clean Energy Research Lab. and the frequency controller is implemented in the LabVIEW setup to control the synchronous generator for the frequency to control the system frequency. And you can see here, whenever there is a change in the load demand, the synchronous generator is trying to maintain the frequency and to stabilize the frequency to 50 hertz. And this dip and the overshoot shows you that there is a change in the load demand, and the control actions shown here. And the LabVIEW pattern here, it shows you to enable either RNN based of frequency control or FORNN type of a frequency control that you wanted to select. And this is a case of for a FORNN. If we compare the results of RNN and FORNN here, the results are for FORNN will be very faster compared to the RNN case. And we also implemented FORNN for the case of when we have a penetration of our solar PV, and you can see that the frequency of the system maintained tightly whenever there have a frequency the PV injection into the system. So the orange line here shows you the PV injections, and this is the synchronous generator response to mitigate this frequency overshoot or undershoot in the system, so thereby maintaining the system frequency. And this is a case, it shows that for the case of a random change in the load demand, the response of the synchronous generator and the response of the system frequency still can be maintained. And this orange line shows you the speed of the synchronous generator changes to maintain the frequency. Yeah, to conclude, so the smart contract participation matrix has been implemented for the system in order to regulate the system frequency when the trading is happening within the microgrid, as well as during this case, the prosumers are participating in both the energy trading market as well as in the grid ancillary market in order to get the more profit. And by establishing the peer-to-peer energy trading concepts into the microgrid, the user can get more profit than the conventional way, and then the level of the power system is maintained here. So further, the study can be further extended to maintain the voltage of the system and observe what happens, the voltage stability of the system whenever the trading is happening. And the study can be furthered by having the advanced control techniques to improve the adaptiveness of the system whenever we have the peer-to-peer energy trading in stack of multiple services like a demand response, all those things. So this is the upcoming study of this particular project. Yeah, this is the references that we have published related to the works that I have presented. Some of the papers that you can refer. Yeah, thanks. If you have any questions, yeah, I'm here to answer. Yeah, thanks. Yes, I'm done. Yeah, I'm done, Dr. Singh. I'm done. Thank you. Okay. Thank you, Prof. Yeah, thank you for inviting, and thank you once again, everyone. Yeah.